So let me start with some notation. Oops. For me, I will take two different prime numbers. F is a p-adic field. And then I fix a quasi-split reductive group. And I will also choose an auxiliary Iwahori model over OF, which is the ring of integers of F. And I'm also going to fix some coefficients that are going to be a Seidel algebra. And actually, I will start with some motivation or some like presenting the ideal picture. But for most of the talk, it will actually be L torsion. And okay, so let me start with the motivation and then tell you about the results, or tell you about the main results. So we already know the stack of L parameters, we already know Bun G, we already know Isoc, but let me still fix some notation. So I will let P lambda just be perfect complexes on power G lambda, and then I'm gonna talk about the spectral side. Since in my talk, the spectral side doesn't play such a big role, I'm not going to be very careful on what I put in here. We have an analytic category, which is a version of sheaves on Bun G, and then we know that there's like an étale version, a Lees version, a relative version. It's motivation, so you can feel free to put any category you want there, because it's still motivation, and here we can put sheaves on Isoc. And in the ideal picture, which is part of what we're trying to draw in this conference, there should be some spectral category that is acted by P lambda. There should be some analytic category, which is acted by P lambda, and we already know this exists. But the schematic category should also have a natural spectral action, and there's already some work in progress in this direction in equal characteristics. So when F characteristic of F is positive, then there's work by Etab, Gatesbury, Genestier, and Laforgue. Endowing this with a spectral action, right? So I guess this is Fark-Scholze. This is maybe a tautology, if you set up your formalism correctly. And okay, so we have these three categories, and they should have a P lambda action. And in the ideal world, they're actually, so I guess one of the lecture series was about this direction, right? This is the series of Hamann. And the other series is about this direction, at least on the tame part, and this is Ju. And I guess if you believe that both programs are successful, then you would also expect that there is a third arrow here, and this is the one where I want to tell you about. So the ideal picture, the three categories receive an action by P lambda, and all of them, there are canonical ways of writing equivalence between them that are linear with respect to these actions. And I will be brief about this, but we can ask, why should we care about this? And I'm going to give you two reasons. The first reason is that the two sides, I guess in the end, we're interested in relating some form of LLC, right? So this is maybe the below part is automorphic side, and above part is the Gallo side. And as long as one of them is an equivalence, we would be very happy, right? That's what we're trying to show in this summit, or discuss the proof of. But actually, the two different versions of LLC that you can consider relate different to different mathematical objects. So on one side you have the generic fiber of Shimura varieties. And a special fiber. So the analytic world talks faster to the generic fiber of Shimura varieties, and the schematic world talks faster to the special fiber of Shimura varieties. For example, in analytic world, some people care about p-adic period domains. So this is, maybe you should ask him, because it's work in progress, but they have announced that there's work in progress on how to endow the schematic side, or this like D of Isoc, sheaves on Isoc, with a canonical spectral action. So in fact, CLLC, we already have a very nice spectral action, and in Isoc, they can make sense of this in in equal characteristic. Yeah. So if your p-adic field is characteristic, so maybe. Yes, so an analytic side talks to p-adic period domains, and the schematic side, maybe an analog object that it talks to are affine linealistic varieties. And you can imagine that if you have an equivalence on one side and you have this functor, then you can transfer information from saying we know something about p-adic period domains, then what can we deduce something about ADLBs, or vice versa. Right? So this is one reason I can give, like, why one should care about this functor. And the second one is, actually, we don't just want to prove that two categories are equivalent, we want to study the equivalence, right? And even if you know you have some actual equivalence, you might want to make it more explicit. And what I want to convince you is that there are also different tools you can use from one side or the other that can help you understand this equivalence. So, different tools. And remarkably, on the analytic side, we have Eisenstein series. Because we can make better sense of what Bun B looks like. B bundles on the Frank-Fontaine curve are, in general, a better behaved gadget than B isocrystals. And on the schematic side, we also have categorical trace techniques. Okay, so that's maybe what I want to say about the motivation of this project, and let me just state the main result. And this is with Hamann, Ivanov, Joao, and Lourenço. Okay, Lourenço, sorry. If it is a joke, but maybe only some people know the reference. So if lambda is a torsion Seidel algebra, then we can exhibit equivalence in Lincat. And this functor that I'm talking about. And moreover, this functor is T-exact. And I don't really want to discuss the Perverse T structures. I'm just going to tell you a little bit about it, and maybe there will be other moments to discuss in office hours or something like this, but let me just put what matches what. On the schematic side, you can talk about the perverse T structure that Xinwen made sense of in his paper. And when you pass across the functor, you get the so-called Hadal T structure that David Hansen discusses in his Beijing notes. And there's also, both sides actually turn out to have two T structures. And this morning we already saw that there is an exceptional T structure. So Xinwen discussed an exceptional T structure. And this exceptional T structure, an Isoc, will match the perverse T structure on Bun G. And maybe you remember Xinwen was saying that there's like a comment about like there's some reversal of topologies happening when you kind of consider this exceptional T structure. And that's like one manifestation of it. This exceptional T structure you consider an Isoc really corresponds on the other side to the more natural perverse T structure you would put on Bun G, where you put the actual dimensions of Bun G B when you kind of consider your perversity function. Okay. So the main purpose of my first talk is to give you a sketch of the construction of this functor. And then in the second talk, I'll try to say some words on why this is an equivalence. So before I give you the actual construction of this functor, I can discuss the naive construction. And most of what I will say is actually about the naive construction because the actual construction is very painful. And somehow I'm going to tell you this is how it goes, and you have to carry a colimit everywhere. So you'll see that happen. But let me just actually say more about the naive construction. Okay, so the first thing is we're in a schematic world, and then we have to somehow go to the analytic world, right, to construct this functor. And there is one way of doing that via Scholz's analytification functors. So if I start with any pre-stack, or I guess, if I start with any pre-stack, I can attach to it a B-stack. And it essentially goes by the formula if you want to plug in an RR plus, right? If a B-stack inputs perfectoid pairs, perfectoid Hoover pairs, and you have to say what happens to it. It's just whatever you were doing on the spectrum of R in your original pre-stack, except you also have to sheafify. And when you do this, then, you will get a B-stack, but moreover, Scholz defines an analytification functor. C star from d et al, x lambda to d et al, x big diamond of lambda. And he proves several very nice properties of it when X is a scheme. So for example, this map is always fully faithful and compatible with pullbacks. And if you have a map of schemes where you can define a lower Schrick, then this is also compatible with lower Schrick. Okay, so this is how we're going to start. This is our starting point to go from the schematic world to the analytic world. Because we started with some schematic sheaves, and now we are in analytic sheaves, and then you can think that you can play in the six-functor formalism of analytic sheaves to construct a functor to Bun G. Right? So, well, we know also that it was already studied in this summit that like there is a reversal of topologies, right? The topology of Isoc does not correspond to the topology of Bun G. And in particular, you cannot expect that the functor is constructed from a map of stacks, right? But what turns out to be true is that there is a very nice correspondence of stacks. Where here you put Isoc G and you take its big diamond and you put this object Bun G mer and you put Bun G in here. And there are two maps, gamma and sigma, And this gamma stands for generic Newton polygon, and sigma stands for special Newton polygon. And let me review a little bit of how this correspondence is constructed. Well, everyone in this room already knows this, but Bun G are just G bundles on Y0 infinity of R plus Frobenius structure. And what is Isoc G? Big diamond. Well, Isoc G big diamond, what you have to do is you go back to this formula, like on RR plus points, you have to put Isoc of spec R, right? So what is this? So this is G bundles on spec of WR 1 over pi plus Frobenius structure, right? Because this is maybe what happens on an R plus points up to sheafification. And the magic thing is that, well, you have this curve Y0 infinity, and something you can do is look at its closed version, where instead of taking the open interval, you take closed interval at 0. And this is, oops, I need this subset on the other side. So here you have something like this. And the funny thing is, if you take the divisor in which p equals 0 in this curve, and you take the completion, well, usually you would get b the ram, but b the ram in characteristic p is just the Witt vectors. So you can think that spec of W of R is nothing but the completion of this at the locus where pi equals 0. And okay, if you want to be very formal and precise about like this being a map of spaces, then you have to be careful on what you put here and there, but this eventually makes sense. So if I want to get out of something, this already starts looking like this correspondence. Because the moment I invert pi in the spectrum of WR, I will start getting isocrystals. And here I can just go directly to Bun G. I can take a G bundle. Where's my laser? No. This? Yeah, okay. So I can start with some G bundle over here and restrict it to over here, and this will be what this map is doing. Or I can start with some G bundle over here and restrict it to be over here. And that's almost okay, except this will not give you really Bun G mer, and it will not give you Isoc. It will give you another object. It will give you Stukas, and you'll also get Stukas over here. So if you want to get Isoc, you just have to invert by pi, but algebraically, right? So here the emphasis is this is a locus inside of here. What pi is different from 0, but this is done in an analytic way, whereas we really want to enforce that pi is meromorphic, and hence the name Bun G mer. So I'll just write some symbols, and this should make sense, and there's a way of making sense, but I don't want to spend too much time saying how this makes sense, but I just want to write this here. And here you can still put spec of WR 1 over pi. Okay? And then the proposal is to just put G bundles there together with Frobenius structure, and if you do that recipe, then you get exactly to the diagram that I drew over here. And okay, so this approach was introduced by myself, Ivanov and Zillinger, of thinking about this object over here, this Bun G mer. Okay, so then what do we do? Then the construction of the naive functor is, I'm going to take sigma lower Schrick, I'm going to pull back, and I'm going to analytify. And this is supposed to give me a functor starting from d et al. Of Isoc that goes to d et al. Of Isoc G, and then goes to d Bun G. Well, I guess this perspective of this naive functor was already advertised in my paper with Ivanov and Zillinger, but we actually run into very hairy technical problems with this definition. And the first problem is, does this functor sigma Schrick exist? And the second problem is the category we really want to study equal to d et al. Of Isoc G? And today, up to today, I still don't know if the answer to any of these two questions is true or false. Well, if you have some experience with six functor formalisms, you know that really showing that a lower Schrick exists is contentful. It usually implies some sort of finiteness conditions, and in the schematic world, sometimes, the kind of condition that comes in is being finite presentation. In analytic geometry, you have to kind of control the underlying topological space of the fibers and the dimension of the fibers, and there's a technical term being representable in locally spatial diamonds of finite transcendence degree that allows you to tell, okay, yes, this really is Schrickable. And Bun G mer, it's probably not representable in locally spatial diamonds. Even the diagonal is horrible. So I still don't know if that thing exists. But yeah, I guess the claim is that in this project with my co-authors, we tackle these two problems. And the solution comes inspired in the treatment. Questions? Yes. Oh, sorry. So I guess Mingjia introduced sheaves, right, last week, and it was obtained via some CAN extensions. But that's actually the d et al., the one that analytification is constructed for, is defined via B descent. And it's always a left complete category. And so, okay, I'm planning to say more about this later in the talk. Okay, the solution is to treat Bun G mer as a Sind Artenstack. And maybe you're not so familiar with the term Sind, or maybe you already read Xingwen's paper and then you are familiar with this, but this is the contraction of the word sifted and int, right? And the way you should think about it is that Bun G mer admits presentation as a Sind colimit of int objects, all of which are fine, right? And I guess I'm going to talk a little bit more about this, but the way you should think about it is you have Isoc G, you can resolve it by Stukas, and if you take the check nerve of this, then you will get a lot of, Hecke correspondences between Stukas, and each of these Hecke correspondences with Stukas, you can bound the pole. And the moment you bound the pole, then you are a nice object. And this is maybe where the Artin-Bistak part will come. So it is kind of horribly infinite dimensional, but at least it is horribly infinite dimensional in a way that we can categorically manipulate. It's the thing that you should kind of take out of it. Okay. Now I'm going to go and talk about what Arnaud asked about. So et al. Sheaves on schemes. I guess, yeah, I'm going to tell you how we try to address these two problems for the rest of the talk. And this is pointing towards the actual construction of the functor. And where do I see my time? Sorry. Maybe, yes. Until when do I have?
2:45.
Okay.
4:47. You have like 35 minutes.
Okay. Okay, so let me talk about étale sheaves and schemes. So last week, Mingja introduced a sheaf that in my world I'm going to start calling sheaf streak to make distinction from another object that also shows up called sheaf star. But okay, so maybe let me say there are actually you have maybe all the theories are sort of built out of this kind of extension procedures, and you can start on the maybe like the most well-behaved world, which are perfectly finally presented schemes. Then you can go to quasi-compact, quasi-paraded schemes, and then you can go to the generality of étale stacks. And then there are three theories. Well, there are actually more than three theories, but in our paper, three theories play a role. The first one is the étale, and this is the one for which C star is defined. And there's another that I'm going to call sheaf star, which is intermediate. So it doesn't play a big role, but it is an intermediary between the third theory, which we care about, is sheaf shriek. And this is maybe the one studied last week. Okay. Now, the three theories actually agree on PFP schemes. So all agree on PFP. Oops. But you already see the difference when you go to QCQS schemes. So on QCQS schemes, sheaf star is given by a left can extension over upper star of sheaf star. And here you have to remember that like any QCQS scheme can be approximated, can be kind of written, or affine QCQS scheme, or yeah, it's true even for QCQS scheme, can be seen as a limit of like perfectly finally presented ones. And you do a left can extension with respect to that, and sheaf shriek is a similar left can extension where you put the shriek functor instead. And finally, the étale of X is actually the left completion of sheaf star. And well, we always have a comparison or a natural transformation from sheaf star to the étale. But they do not always agree. And then what do you have to do? So now I told you what happened to the three theories on QCQS schemes. Then you have to say what happens on étale stacks. And on étale stacks, they are all right can extensions. And maybe in some finite dimensional cases, you can control the difference between this guy and this guy. But I think when you pass to étale stacks, I get very confused if there's any comparison at all. I still don't know what is the relation between the étale on Isoc and sheaf star on Isoc. But then even if you compare that, you still have to compare with sheaf shriek on Isoc. And that also seems even more confusing. Okay, so you have these three theories, and they were obtained in very abstract methods. The next question is, how do I access these categories, right? Like, how can I start studying them? Like, Xingwen is able to say something, or you can say many meaningful things about sheaves on Isoc, and the question is, how did we start accessing that category? And the way I think about it is there is a finiteness hierarchy. I think it might, so this, I get confused. It might still be true that, yeah, let me not guess on the spot. But it might still be true that, like, if you pass to a tile stacks, you get some left completion, but. Yeah. Yeah, but there might be some abstract statement saying that if, like, left completion commutes with colimits and things like this, if you have this, then it's true, but yeah, let me not. But, okay. I guess my point is the one we really care about is this. And already, over QCQS schemes, they differ. Sometimes you can make them, like sheaf trig theory, be equivalent to sheaf star theory, but non-canonically. There's like no canonical way of doing that. And this complicates things if you want to pass to a tile stacks, right? Because there you actually would want to compare them canonically. And okay, so let me talk about this finiteness hierarchy. So as I told you, we have these three very abstract theories. The question is, how do we access them? And we do it in stages. So we have PFP algebraic spaces. Then there are something that already Xingwen introduced called standard Placid algebraic spaces. Then you can go to some objects that are infinite dimensional by construction, but still behave like finite dimensional, what are like very placid stacks. And then you can take int completions of this so that you get int very placid stacks. Okay, so here we adjoin filter limits. And finally, you can talk about sin very placid stacks. And okay, how do you access this? You start studying what happens here, then with some patience you understand what happens here, more patience, more patience. By this time you don't have patience anymore, but you still understand something perhaps. But the picture you should have in mind is Isoc lives in here. And the reason why Isoc lives in here is because the stack of Stukas with the Wahori level lives in here and it has an improper map. And the reason this guy lives in here is because this admits a presentation as a colimit as you range over mu of the bounded pieces, bounded by mu. And the reason the bounded pieces, so this is why this guy is int, and it's because you have a Stuka bounded by mu that lives in here. And the reason why this one lives in here is because you can resolve this by the loop group bounded by mu. And this resolution is by the presentation that Stuka bounded by mu is the loop group modulo the positive loop group. And the positive loop group, oops. Yes, thank you. This has some large unipotent part and some finite dimensional group. And finally, the reason the loop group is here is because it admits a map to the flag variety bounded by mu, or maybe you can use words in the veil group. And again, this has fibers that are essentially per-unipotent. Yeah, so I precisely didn't want to remind what they were, so I was just giving examples. So, but I can say in words, roughly. So sin very placid is something that has an improper resolution by something that is int very placid. And something that is int very placid is something that has an int resolution by something that is very placid. And something is very placid if it has a pro-unipotent resolution by something that is standard placid. And something is standard placid is if it has essentially pro-unipotent map to something that is perfectly finally presented. I know it sounds like a poem, but I didn't make this one. Okay, okay, definition, if X is a sin very placid stack, we say a map from C to X is a bounded piece if C is very placid and F is in PFP proper. Okay, and the way you should think about it is you have Isoc, which is sin very placid, and we want to look at a bounded piece of it, and a prototypical example of a bounded piece is exactly something like this. So this one is very placid, but the map to Isoc is still in PFP proper. And the point is these very placid stacks are actually something we can control the sheaf theory better on. So past very placid, I get very confused. It's all just colimits everywhere. But on very placid stacks, one can still have some control and say kind of some more concrete things. Okay. And okay, I made this definition of bounded piece, and I can consider a full subcategory of étale stacks over X, right? So I define if X is in very placid, then I have bounded pieces, and I can collect all of them as a subcategory of étale stacks. So this is the subcategory of bounded pieces. And maybe here's a fact. Okay, so if X is sin very placid, then example to think about is, of course, Isoc. And maybe
Sorry, and a good example of very placid is bounded sweepers?
yes. You can take an element either mu, or you can take an element of the veil group and bound by that, but I want the closed piece. I really want it to be proper, so, well, there's a very small lie here. You need slightly stronger than sin very placid, but Isoc satisfies this anyways. Then the dual has an expression as a colimit over the bounded pieces, ranging over, what is this? Lower streak, or because, yeah, every time you have a bounded piece, the map is proper by definition. Like, for it to be a bounded piece, the map has to be proper, and then all transition maps between them are proper maps as well. And so F lower streak is the same thing as F lower star. And here, what you see is already sheaf star of Y. Okay, so this is something that one shows. And what is the point? This sheaf star category, I can already send it to D et al. Because I always have a natural transformation between this and an actual D et al. And then if I want to construct a functor, I can now analytify this and take colimit over these analytifications. So this is what I want to do. Okay, so then maybe now I want another definition. And we made in the paper, we make a more general definition in terms of something we call sin-dagger correspondences, but let me just simplify our lives for this talk and just give you a definition for Isoc. So given some y in this abstract category, Isoc G, we're going to say we let y gamma, you can think of it some sort of gamma transform, is going to be this. Bun G mer. Okay, so we define this, and we also define, we let sigma y from y gamma to essentially be the composition. And we're going to say that y gamma is sigma compatible if sigma y is shrinkable. Okay, and I'm going to denote the category of sigma compatible pieces. So sigma compatible pieces, sigma compatible bounded pieces are a subcategory of the actual bounded pieces.
So a priori, does one know anything about sigma y that is like representable with the spatial dimensions?
That's what I'm going to talk about. Okay. Yeah. So really here you just made an abstract definition. Like I have some bounded piece, I take its y transform, sorry, its gamma transform, and I have sigma y map to Bun G, and I just ask that it's shrinkable. And you can make this subcategory. And okay, so more concretely, there are some examples of this y transform, and this underlies the theorem with Ivanov and Zillinger. If you take the local stukas that Xingwen discussed, and you bound by some W or some mu, and you take its gamma transform, then you're going to get some familiar object in the analytic world, which are the analytic stukas from the Berkeley notes bounded by W, except that we can only look at this at special fiber. So it's really just the stack of stukas on the special fiber, but bounded by W. Okay, and theorem, the map from stuka, analytic, bounded by W, IFP, to 1G. Is actually representable in locally spatial diamonds. And shrinkable. Okay, so this tells us that I guess at least we have a nice resolution of Isoc by bounded pieces that are actually shrinkable or sigma compatible. And okay, some category nonsense that we have to deal with is out of that information, then one can really show. So lemma.
Is it possible for you to write horizontally using the whole space so you can scroll?
I think we tried this in a different talk. Like this? Like this?
Make it a little smaller and use the whole horizontal space you have. Or just keep going.
So right now you have 3 words per line.
So now I go down here. Okay, so this for W and W. Maybe I can fit 5 words. And so, okay, the statement is, yeah, using that this is representable in locally spatial diamonds and shrinkable, then this will be a sigma compatible bounded piece, and maybe the more important statement is that those are enough. Those are enough to, like, I mean, a priori, Isoc, you have to take colimit over so many things, but the point is this really is a resolution of Isoc, and it's sort of cofinal there, and then the point is that this category, Isoc G, if you pass to its dual category, then this can really be taken as a colimit among this type of object. And you might ask me, why do I have to care about this whole business about bounded pieces and being sigma shrinkable and something like that? Really, what you should think of is the actual shrinkability of Stukas is defined, and you could have said, I start my life with an Iwahori, I resolve with this Iwahori, and I construct my functor with respect to the Iwahori. And this is just a technical device to show that it doesn't depend on the Iwahori, right? So it is true that this colimit holds, but it also holds like the colimit at the level just of like very explicit Stukas, like take a specific W's and take the Hecke stack and take many words, and those are all shrinkable. But this is a device to kind of deal with the question of whether the functor depends on the Iwahori that you started with, and the answer is that it doesn't. Okay. So now we're ready to talk about the take 2. So I gave you the naive definition of this functor. Oh, but is it I have 5 minutes or 12 minutes? Okay. So now I can really tell you what the actual functor looks like, now that I have talked about all of this. Okay, so we start with the theorem of Ju. So Ju constructs a canonical duality between sheaf, shriek, Isoc, and its dual, so an equivalence. And so whatever pitch is just going to be the composition of Ju's duality with some other functor that is maybe called pitch dual. Okay, so if I want to tell you what this guy is doing, then I just need to tell you what this one is doing. Okay? But I guess I already prepared you for this, right? Because I already gave you an expression of the dual as a colimit of these things. So if I want to give you a map from a colimit of categories, then I have to give you a map for each category and argue that these are all compatible in a coherent way. Right? So whatever this functor is, it's just going to be a colimit over sigma compatible bounded pieces. Thank you. of some other functor like this. Okay, and now I can really write what this guy is. So this colimit is now over this sheaf star theory. Right. So I start in this category. Then I can just pass to left completion to go to this category. Then I can take analytification, shows us analytification functor. Then I can pull back by y gamma, and this lands in the étal of the gamma transform of my bounded piece. And then I can finally shrink, because by hypothesis, the map from y gamma to Bun G is shrinkable. So now I finally did tell you what this, but I still have to explain a little why this is compatible as you range over this category, right? Because this is now, I'm presenting to you a functor as a colimit of functors that are ranging over this category, and then you have to do this in a very functorial way. So technical point. This guy should be functorial. Okay, and I guess here I give you the functor in 4 steps. Like there's this, there's this, there's this, there's this. And some of them are easier to make functorial, or when I say easier, it's more like there's more literature available that you can just cite. So I guess there's the passage to completion should be fine. Pulling back is also fine, because pulling back all happened within a 6-functor formalism, right? It all happened in the analytic world, so it's already in a 6-functor formalism. And this one is also fine. So these ones are easy. And at least for us, making this compatible with C star required more work. And the reason this requires more work is, I told you that there is this very nice analytification functor that Schulze discusses, and well, it is compatible with pullback, and I also told you that if you have maps of finally presented schemes, it is compatible with lower shriek. But then there's the problem of here we're actually playing with stacks. And you really need kind of compatibility with lower shriek at the level of stacks. And this is maybe the thing that was maybe more painful for us. So let me, sorry, I'm supposed to be able to read the clock, but 7, okay. So let me make a definition. Okay, so I guess what I'm trying to convince you is this part is easy, and this we put more work on. And I'm going to explain a little bit of what work came in. So definition. A tall stack is resilient if okay, so at the beginning of the talk, I told you something about analytification, and I told you there's this big diamond and there's this analytification functor. And now I want to emphasize, there was some sheafification process when I told you about this construction. And I want to identify between 2 sheafification processes, one for the Proetal topology and one for the V topology. And we're going to say that an étal stack is resilient if when you sheafify with the Proetal topology, it is already a B sheaf or a B stack. Okay, and we're gonna also say, so I'm going to say that a map of stacks x1 to x2 is Artin if there is a map y to x1 that is cohomologically smooth representable PFP and surjective such that y2x2 is also representable and PFP. Okay? So you should think of this as smooth locally, it is representable PFP. And then finally, I want to finish with this theorem. There is a canonical natural transformation of 6 functor formalisms. D tau lambda to D tau lambda defined on C comma E. And I'm going to give you two options for what E1 and E2 are. But C is just going to be the category of resilient étale stacks. And E1 is going to be the analytifiable maps. And E2 is going to be the Artin maps. And this lives inside of here. So what happened? When we made this notion of analytifiable maps, we essentially said, for which kind of maps can we make lower Schrick commute with analytification? And we just tried our hardest to get the most general result we could. So it's a very ad hoc class, is whatever we can prove commutes with lower Schrick. And I don't know, we had some hopes that like maybe someone will need more and more analytifiable maps to commute them with lower Schrick, so we just try our best to make the larger set of edges for which analytification behaves well with respect to lower Schrick. And Artin maps are the only maps that actually matter for proving the equivalence between Isoc and Bun G. And it's quite easy to show that Artin maps are analytifiable. Okay, so I think I'll stop here for questions.